right? Let's look on what we call the hyperbolic function. The hyperbola. This is the hyperbolic function, right? In this function, our x is a denominator. Our x is a denominator. It's given by this. It's a over x. That's a hyperbolic function. So our x is a denominator. So obvious, if x is a denominator, x must not be equal to 0. That's the domain for this function. X must not be equal to 0. Right, the most important thing about this function is that it has got the asymptotes. For instance, let's make y to be 0. We are making y to be 0. We want to solve for x because we are talking about x and y, x, y. So let's solve for x. To solve for x here, we multiply by x on both sides. So here we are going to have 0, which means a is equal to 0. We were to solve for x, so x is no longer existing, which means y must not be equal to 0. Y must not be equal to 0. X must not be equal to 0. Y must not be equal to 0. It's x now. X must not be equal to 0. So this is a restriction for this function. So a restriction in terms of y, we call it a range. Y can be any value. You can put any value in the place of y, but y must not be equal to 0. That's how to write a range for that function. Or for the domain. For the domain, it's x x can be any value, but x must not be equal to 0. So in this case, we are saying this is our range. That's our range, and this is our domain. That's our domain. These are the restrictions that will give us what we call the asymptotes. Let's say, for instance, we've got this graph. G at x is equal to 2 over x, and you are to sketch this function, right? X is to y, negative 2, negative 1, 0, 1, 2. Let's substitute. You put a negative 2 in the place of x. The answer will be negative 1. Put negative 1 here. We are going to have negative 2. Put 0. That will be undefined because we can't have 0 as a denominator. It won't exist. Let's put 1. The answer will be 2. When you put 2, we are going to get 1. Let's sketch the graph. Right there. It's 1, 2, negative 1, negative 2, negative 1, negative 2. Right. If x is equal to negative 2, y is equal to negative 1. It's here. If x is equal to negative 1, y is equal to negative 2. That point that is there. Right. If x is equal to 0, this is undefined. If x is equal to 1, y is equal to positive 2. It's up there. If x is equal to 2, y is equal to positive 1. So remember that we are saying if x is equal to 0, this won't exist. In other words, x is equal to 0 on the y-axis. X is equal to 0 on the y-axis. Therefore, our graph won't touch the y-axis. It doesn't exist on the y-axis. Same thing here. It won't touch the x-axis. Right, let's capture the graph. It approaches here, but it doesn't touch. Also here, goes up like that, but it doesn't touch. It doesn't touch the x-axis, it doesn't touch the y-axis. This is the function of g. It's the function of g. This and that, it's one and the same function. 1 is to 2, 2 is to 1. Here, negative 1 is to negative 2, negative 2 is to negative 1. Right. When you look here, we have negative 2 is to negative 1, negative 1 is to negative 2. So here we've got positive 1 is to 2, 2 is to 1. Same graph. In other words, this is a reflection. This graph is as reflected to the first quadrant. It's the image of this. It's one and the same graph. Same time. As you sketch on the other quadrant, it reflects on the other quadrant. That's a hyperbolic function. Right? We've got the y-axis where we said our graph must not touch the y-axis. Also, it mustn't touch the x-axis. We do not touch where x is equal to 0. And we do not touch where y is equal to 0. X is equal to 0 is our asymptote. Y is equal to 0 is our asymptote. These are our asymptotes. Because it's where our graph will be undefined. It's where our graph will be undefined. The value of x where this graph will be undefined, it's where x is equal to 0. The value of y that will make this graph not to exist, it is when y is equal to 0 on the x-axis. Therefore, x is equal to 0. That's a vertical line. It's a vertical line. So that means it's a vertical asymptote. Vertical asymptote. It's a vertical asymptote. Right. Y is equal to 0. Y is equal to 0 on the x-axis, which means this is our horizontal asymptote. It's an asymptote that blocks us from touching the horizontal line. It's a horizontal asymptote. So our graph does not exist where x is equal to 0. And our graph does not exist where y is equal to 0. That's what the asymptote tells us about. And then, for this graph to always exist, that's a restriction. We are now restricting our graph to exist for both y and x. That's domain and range. We are saying this graph won't exist where x is equal to 0 for this graph to always exist, it mustn't touches where x is equal to 0. In other words, x can be any value. X can be any value, but that value must not be equal to 0. X must not be equal to 0. Again, for the range, that's our domain. For the range, we mustn't touch the x-axis for this graph to always exist. So, in other words, here y must not be equal to 0. Y can be any value, but that value mustn't be equal to 0. So, that's how to find all these. This is a restriction. These are our asymptotes. It's when our graph doesn't exist. For this graph to exist, you write a restriction that we call it a domain and a range. Right. Let us now check on what will happen if that value up there is negative. Because when you look here, our value up there, the value of A is positive. A is positive here. Let's write it here. A is positive. Let's see what will happen if we have a negative value of A there. Let's call it f at x equals negative 2 over x. Let's draw our table. We are now going to check what will happen if A is negative. It's x, y, negative 2, 0, 1, 2. We are to put negative 2 there, the answer will be positive 1. Put negative 1 here, the answer will be positive 2. Put 0, it's undefined. Put 1, it's negative 2. Put 2, that's negative 1. Let's sketch the graph. Let's use this space. Right, these are the x-axis, y-axis, 1, 2. Right, let's plot our points. Negative 2 is to 1. Negative 2 is to 1, there is a point. Negative 1 is to positive 2. There it is. We do not touch where x is equal to 0. That is the y-axis. It will be undefined. 1 is to negative 2. 1 is to negative 2. There is the point. 2 is to negative 1. 2 is to negative 1. And then let's sketch our graph. Remember, it doesn't touch the y-axis. Also here. Also, it doesn't touch the x-axis and the y-axis. So the points here, it's negative 1 is to 2. Here we have negative 2 is to 1. 1 is to negative 2. Here, 2 is to negative 1. This is the function of f. Right, let's compare the two functions. The domain and the range are still the same. We do not touch the x-axis, we do not touch the y-axis, which means our horizontal asymptote would be the same as we did on this graph where A is positive, right? I just want us to check and compare the two functions where a is negative. Our a here is negative. Our a is negative. Comparing the two functions, this one here, x is negative 1, y is positive 2. And when x is increasing, when we go to that direction, x is negative 1, y is positive 2. From 1 to positive 2, so we are going up. Same thing here. From 1, x is 1, y is negative 2. So from negative 2 to negative 1, we are increasing. We are increasing here. That means if a is less than 0, if a is less than 0, as you can see, a is negative. That will mean the hyperbolic function will be increasing. That's an increasing function. That's an increasing function. Whereas here, we've got negative 2, negative 1. We are increasing with the values of x. But looking at the values of y, from negative 1 to negative 2, we are going down. Again, from 2, as x is increasing, from 2 to positive 1, we are decreasing. Also here. Therefore, this means that if a is positive, our function will be decreasing. That's a decreasing function. That's a decreasing function. Right. This function is decreasing. It's decreasing. We are saying it's a decreasing function simply because as x increases, y is going down. Here, this is an increasing function. As s increases, y is also increasing. So if they are both increasing, we call it an increasing function. But if x is increasing, whereas y is decreasing, that would be a decreasing function. Right, let's see now what will happen if we are to shift this graph. Let's shift the graph. We want to shift it for both vertical and horizontal. So when you shift both vertical and horizontal, that means you can shift this graph towards right and also up or down. Therefore, the equation will be given by a over x. We are shifting, it's either positive or negative. So it's x minus p. Remember, this is our y. Y is equal to this. So if you want to shift this vertical, you have to add something to our y. That's plus q. Right. Let's see if we can be able to solve this graph if our x is equal to p. If we are to put p in the place of x, then let's say you have y is equal to a over p. We are substituting by p in the place of x, p minus p plus q. It's plus q. This means that we are going to have a over 0. That doesn't exist. A number over 0, it's undefined. Right, again, let's put q in the place of y. It's a over x minus p. We want to solve for x plus q. we are putting q in the place of y. We are putting this shift in the place of y, right? A over x minus p will be equal to q minus q. Therefore, A over x minus p will be equal to 0. We want to solve for x, we multiply by this on both sides. Therefore, we're going to have A equals 0 into x minus p. So 0 times that, it's 0. X is no longer existing. Therefore, y, we said y, we have let y to be q. So if y is equal to q, the hyperbolic function won't exist. If x is equal to p, the hyperbolic function won't exist. Right. Here, we said x is equal to 0. It's a vertical asymptote, which means it's where our graph won't exist. And then now, if x is equal to p, this graph won't exist. Therefore, this is our vertical asymptote. That value of x, if we are saying x is equal to p, that will be our vertical asymptote. Let's write it. Right, we have this function a over x minus p plus q. So if we are to make x to be p, if x is equal to p, the graph won't exist. Therefore, this will be our vertical asymptote. Remember that when we talk of a vertical asymptote, when we say x is equal to something, you are talking about a vertical line. If x is equal to something, that's a vertical line. If we are to make y to be q, again, if y is equal to q, if y is equal to q, again, this won't exist. This is our horizontal. Horizontal asymptote. So when you say y is equal to, you are talking about a horizontal line. If you say x is equal to, that's a vertical line. Remember that these are the shift. X minus p, we are shifting horizontal. We are shifting horizontal. So p represent a horizontal shift. It's a horizontal shift. Whereas when you look here, we've got y is equal to this plus something. So that's a vertical shift. Q is a vertical shift. Right. X is equal to P is a vertical asymptote. But P is a horizontal shift. We are shifting horizontal, but it's a vertical asymptote. This is a horizontal asymptote, which is our vertical shift. Q represents our vertical shift. Right, let's try to make an example of this. Let's say you were to write the domain and the range for that. This is our asymptote. It's where our graph won't exist. Which means for our graph to exist, we need to have a domain and a range, so that we are going to write a restriction for it to exist. For this graph to exist, you just go to your vertical asymptote and you restrict it. X can be any value, but that value must not be equal to P for this graph to exist. Again, for the range is the Y value. Y can be any value, but that value must not be equal to our asymptote. It must not be equal to Q. So that's how to make this function to exist. Right. At first, we had this graph, X and Y. Right, that's our decreasing function. That's our decreasing function. Right, when you look at the two, it's half-half, which would give us this function. Let's say it's a function of g, so it's half-half of that. Therefore, to divide this graph into two equal halves, we use a line. That line, we call it the axis of symmetry. We use a line. To divide this into two equal halves, we use a line, which we call it axis of symmetry. For instance, let's say you are to divide it like that. Using this line. So you have divided this graph into two equal halves. And this line, when you look at this line, it passes through the origin, which means the x-intercept is 0, the y-intercept is 0. If the x-intercept and the y-intercept is 0, that means we have this equation, y is equal to x. Right. Remember, this is a reflection of that. You can also divide this graph like that. We are passing through the origin, going down. So when you look at this, again, the x-intercept is 0, the y-intercept is 0, but this is a decreasing function, which means our equation now will be y is equal to negative, because the gradient is now negative. It's negative, it passes through the origin. So we are going to have the equation like that. It's y is equal to negative x, whereas that one has got a positive gradient. Remember, this is a straight line. A straight line is given by y equals mx plus c. So the y-intercept is 0, the x-intercept is 0. So that's the reason why we are having y equals mx, which is positive 1. In the place of m, we've got positive 1, because this passes through the origin. The gradient is 1. Right. Same graph. Let us shift this graph. Let's shift it this way. We are having f at x is equal to negative 2 over x. Now we are shifting this graph. We want us to shift it 2 units. 2 units up and 1 unit. 1 unit to the right. It's 2 units up, 1 unit to the right. Right. Let's see. If we are to shift that, obviously it will change. Let's say it will change to be h at x. It's a over x minus p plus q. Right. We've got the value of a. The value of a is negative 2. We are shifting this 1 unit to the right. 1 unit to the right. We are shifting this graph 1 unit to the right. It's negative 2. So if you are to shift this graph to that direction, we are shifting it 1 unit to the right. From negative 2 to that. We are shifting it from negative 2. From negative 2. So if you are to shift 1 unit to the right, you move that way. So 1 unit to the right, you are going to minus 1. In other words, you are minusing or you are subtracting. It's x minus 1. 1 unit to the right. If you are to solve for x there, it's x minus 1 equals 0. So x is equal to 1. We are shifting 1 unit towards the positive values of x. So 1 unit to the right will be x is equal to 1. So it's x minus 1. 2 units upward we add because we are going towards the positive values of 1. So it's plus 2. That's how our equation will be looking like. Let's say now you are to write the equations of the asymptotes. Equations of the asymptotes.